Hello and welcome to Maths on the Move, the podcast from maths.org. I'm Rachel Thomas.
And I'm Marianne Freiberger. Now, we are very excited to be going to the European Congress of Mathematics this year in July in Seville, in Spain. It's going to be 5 days of mathematical fun and excitement. Now, the ECM happens every 4 years in an interesting European place, and it alternates with the International Congress for Mathematicians, which happens every 4 years, but in the intervening period.
So, as well as being in an exciting different place in Europe every time, the ECM also is a place where a lot of prizes in mathematics are handed out. For example, the prizes from the European Maths Society, the EMS prizes, they're given to a European mathematician who is younger than 35 in the year the prize is awarded, so haven't turned 35 by the 1st of January this year for these prizes coming up. And what's really interesting is we sat back and planning for the ECM, attending the European Congress of Mathematics this year, we sat back and looked at the list of past prize winners, and we realised so many of them went on to win other big prizes in mathematics, particularly the Fields Medal, which is probably the most famous prize in maths. It is also awarded to younger mathematicians. This case, they have to be under 40 in the year the prize is awarded. And so if we were betting people, we would watch the EMS prize winners this year and put bets on for the Fields Medal for the International Congress of Mathematicians in 2026.
Yes, we would. But before we go off to the bookies, we thought that we were going to celebrate the run-up to this year's ECM in Spain by revisiting some interviews we've done with Fields Medallists in the past who also previously won an EMS prize.
So we start off with Hugo Duminil-Copin, who won a Fields Medal in Helsinki in 2022. And we were lucky enough to attend the International Congress of Mathematicians in Helsinki in 2022. But it was quite an unusual ICM, wasn't it, Marianne?
Yeah, it was, because originally the ICM was meant to be in St. Petersburg, Russia. That was no longer possible after the invasion of Ukraine. And then Helsinki and Finland stepped up quite short notice and agreed to put it on. But it was also unusual because due to uncertainties related to COVID, most attendants attended virtually. So there was 7,000 people attending virtually, and only a few hundred people were actually in Helsinki, including us and the winners of the big prizes. And it was in the run-up to the award of his Fields Medal that we talked to Hugo Duminil-Copin, who won the Fields Medal for his work transforming the mathematical theory of phase transition in statistical physics.
So phase transitions are something that we're actually all familiar with. So we all know that if you cool water down, it freezes to ice when it gets below 0 degrees. So a phase transition is when something complicated, a complicated system like a bunch of water molecules, undergoes some kind of drastic change in its behaviour as some parameter, like the temperature in this case, passes some critical point. So we started off with asking Hugo what drew him to the area of statistical physics that he works in.
I was always interested in physics and math for different reasons, very different ones. I mean, physics because, like many kids, I guess I wanted to understand how the world is occurring around me and why it's working that way. And mathematics because, there is some kind of purity in the mathematical proof and some kind of, when you have a proof of something, it's kind of the end of the story of this thing. Like it's the final answer. It's not entirely true because you have better proofs, you have proofs that are more illuminating and so on. But globally, let's say a proof as something much more final. And for me, who doesn't necessarily have like a lot of self-confidence and things like that, having this kind of being ensured that this is the final answer, that I have a right proof of something, this was something important for me. So I always had this ambivalent, like these two loves in some sense, and not really knowing how to reconcile them. So I chose math at some point because I felt that this need to be sure about what I write was really something important on the long term, to be able to build kind of a castle that will not be a card castle, or I don't know, that could collapse. And it just happened that in my studies, at some point, I was drawn to probability, which I liked very much because my teacher, his name was Jean-François Le Gall, was an amazing lecturer, and really, I mean, you couldn't do anything else. I couldn't do anything less than falling in love with the area. So I started doing a master, and there, surprise, what do I find? I find an area of probability which is exactly trying to understand physical phenomena. So for me, it was like, oh my God, what just happened? What I was looking for years is just in front of me. This is the area which is at the crossroad of the two things I wanted. So for me, it's how it happened. It's not that I aimed for it. It just occurred in front of my eyes that this was just a perfect area for me.
Hugo, you've been recognized for your work on the mathematical theory of phase transitions. Can you give us a description of what a phase transition is and how maths can be used to describe it? Yeah, so I mean, phase transition is not a phenomenon that is specific to math. Actually, it's more of a physical phenomenon. It's when you take a system, usually a complex system, a very big system, let's say gas in the room, or I don't know, a magnet, and you vary its parameter continuously. Let's say you heat it, for instance, or you pressure it, you change the pressure, and you look how the thing evolves. And what happens in most physical systems is that there are what we call critical points, where drastically at this point, the system completely changed behavior. That's what you see with water. If you cool down water at 0 temperature, it gets to ice. And this is brittle. It's always at 0 temperature, whatever the bucket of water you take, at atmospheric pressure. And this drastic change, this is a phase transition. So that's maybe the most famous one with, water to vapor. That happens at 100 degrees. But this is for one system. And in fact, basically any system is undergoing a phase transition at some point. Like most systems are actually having these phase transitions. So this is really not something that comes from mathematics originally. Now, what we do as mathematicians is that we try to understand how these phase transitions occur by kind of making mathematical caricatures of the physical phenomena. And what I do for a living is studying these mathematical caricatures, what we call models of what happens. Looking at your work with these models where you treat the system like a lattice, so is that one of the ways you can mathematically describe it? It's definitely one of the caricatures you make. So let's take a typical example of water. Let's stay with water. You have your molecules of water that are, in a liquid, for instance, they are kind of in continuous position. They don't have to lie on a very regular, and they don't lie on a very regular spaced network or lattice. But in order to study these systems, for the mathematician, it's going to be often, not always, but often simpler to imagine that indeed there is a regularity in the position of the atoms of that. And the beautiful thing is that this is kind of an assumption which is not even verified by physical systems. So it's not that we make an assumption that we cannot prove, it's even something that doesn't occur. But from studying a system with these additional assumptions, which are maybe unphysical in some sense, you still manage to explain
some phenomena that actually are those occurring in physical systems. It's something that is related to a very deep phenomenon, which is one of the things I try to understand as a mathematician, which is the phenomenon of universality. And it's something that says, and it's almost, you could think of it as a wishful thinking, but it actually is satisfied by most systems. It's something that is saying that your models of a physical phenomenon, where the details, the fine details of the model is not really impacting the global behavior of the model. And this is very reassuring for the mathematician and the physicist, because it tells you that if many systems at the end have the same behavior, then it becomes very interesting to choose the simplest example of such systems. And very often the simpler example, the simplest one, is a system that is going to be defined on a lattice, because you will have, translations, you will not have problems of definition because things are discrete. And sometimes you could be afraid that if it's not discrete, maybe you cannot differentiate, or you cannot. So working on a lattice gives you all this freedom of having well-defined objects, having certain nice properties. And at the end, you don't lose anything, because you have this universality kind of motto that tells you that the things you are going to derive, the theorems you are going to derive, in fact, they are very, very robust. And they would also have worked if you have started from a much more complicated system.
So that's really interesting. So it doesn't, you can use a mathematical model, a mathematical description that isn't necessarily representative of the physical reality, but because of this universality, it kind of, you're still going to get still going to end up with the results as if you tried to make a really physically accurate system, but you can get more out of it because it's this simpler, more mathematically.
Yeah, you answer the question much better than I do. It's exactly that. I mean, that's a very good summary of what I said. Yes.
I think people outside of mathematics, for a start, I think a lot of people don't realize that there's these new frontiers always being explored, but also that you need different types of mathematicians, different types of ways of approaching that mountain to get different progress. I
fully agree with that. This is something that I guess maybe the image of the mathematician as a lonely hero that in some sense get his ideas from who knows where and just produce a proof where everybody else was in the dark. I mean, to me, at least, it's not. It's definitely a fair description of some mathematicians, and it's a very, very nice that these people exist. But in my case, it doesn't match at all my vision of mathematics and my way of doing mathematics. I definitely believe that mathematics is much more of a group production, and that you need these people with different experience, different background, different histories. That is going to make it that they are going to think about something that somebody else didn't think about. And it's not that they are better or worse. It's just that they were drawn there by something like more complex than just mathematics that gathers like a lot of what they are and what. So I like very much to interact with people for this reason, because it makes me, exactly enjoy this production that somebody is going to think about that. For me, this idea was just completely doomed, and then the guy in front of me just changed it back to like, just look at it from the other side, and it becomes a marvelous idea. And I'm like, and he's like, thank you, you go for this idea. I'm like, well, I should thank you, because for me, it was just not a good idea at all. So you cannot give me credit for that. And this is this kind of constant interaction and improvement on everybody's idea that makes it in math, and that makes what math is today. So yeah.
So it's a social group activity.
It's very social. Mathematics is a very social activity, much more than what people believe. Also because it's much simpler to be social, because usually you only need to talk, right? You don't need to be in front of a huge experiment, and then the person that you would like to interact with is in front of his huge or her huge experiment on the other side of the world. Here, it's much more sharing ideas, and it can be very fast. It can be 5 minutes over coffee between two talks, and you can already go very far. So I think it's very social, and that makes it very nice.
That was Hugo Duminil-Copin explaining how the very nature of maths, the fact that all you need to do is share ideas rather than complicated technology or something like that, that this makes it a very social activity. Stay tuned for more interviews with EMS prize winners in the run-up to the ECM.
Thanks for listening, and bye for now.